Okay, how you doing? We're going to talk about some division properties of radical expressions. Basically, your generic radical expression is going to be the formula of if you have some k index, you're taking the root of some term, okay, and you're dividing it by something that has the same exact root. For instance, if this is a square, then this also has to be a square. If this is a cube root, then this also has to be a cube root. If this is the fourth root, this also has to be the fourth root. Okay, you cannot have something where it has a fourth root up top and a fifth root down at the bottom and then apply this particular property. You would have to do some other things to this, some manipulations to apply this property. So, some other things we have to talk about here. There's one over here in this little illustration. What this says here is that you must always leave radicals in simplest form, i.e. must remove any factors from a number that are also square numbers. So, if you have a number or a term, for that instance, that has any squared value, you must remove it. That's if we're talking about squares. If it's a cube root, then you must remove cubic roots. If it's a fourth root, then you must remove quartic numbers, essentially. So cubic numbers, quartic numbers, whatever it is, you must remove those from whatever the power of the root is. Okay? So, the next thing we have to talk about here is, so we got this little guy down here thinking that. Then over here we got this guy, okay? He's saying, wonder if that dude knows, can't leave a radical in the denominator of a fraction. So, we go back to this formula and we go, well, how does this make sense then? Well, the point of this is to show that if you're dividing, okay, two terms, that you can write it into this form. And the reason we want this form is because it helps us, it's basically used to rationalize the denominator. This one comes in handy, okay, this form comes in handy if A and B have common factors. And if they have common factors, then we can obviously reduce them. So, on to some examples. So, example 1 here. I've got the square root of 48 divided by 8. So what we're going to do is come up here and we're going to look at the values underneath. 48 and 8, do they have common factors? Is there a factor that is there something that I can break 8, the product of 8, into factors of two other numbers? So can I show this as a product of two factors that this also might have in common? And in this case, yes, we can. So, what I want to utilize in this case, okay, because I'm taking a square root, and a square root, I want to utilize this one. And basically, this one says that I can then rewrite this as simply the square root of 48 divided by 8. And when I go ahead and do this, okay, what I want you to note here, okay, I'm just going to show this a little bit differently. You don't have to show this. But we're going to reduce 48 over 8. So if you're a little bit longer or farther along, okay, how many times does 8 go in the 48? Well, 8 goes in the 48 6 times. So this is really the same thing as the square root of 6. And now that I have this value, what I'm going to check for is, are there any factors that are square numbers? So let me show you what I mean by that. So if I write out all the factors of 6, so basically what are all the numbers that multiply together that make 6? And when I talk about that, I want specific integers. So 1 times 6 makes 6, and 2 times 3 makes 6. These are all the factors of 6 that I'm concerned with because I can't use negatives in this expression. So, none of these numbers are square numbers. So, 1's not a square number, 6 is not a square number, 2 is not a square number, and 3 is not a square number either. So, I can't reduce this anymore because remember, any factor, okay, that is a square number, if I'm talking about a square root, must be removed from this radical. And in this case, no factors are square numbers, so this is now complete. So on to the second example. Now the second example looks like this. It starts off that way here, so we got root 5 divided by root 2. Now, when I do root 5 divided by root 2, it doesn't help me to put it into this form up here. Because if I take a look at the values, 5 and 2, which I could say 5 is A and 2 is B, 5 and 2 do not have common factors whatsoever besides 1, and 1's irrelevant in this case because it's not going to help me do anything. So what I have to do is something called rationalize the denominator, and the way I do that is I remember this. I remember a multiplication property. And the multiplication property states that, or I just remember what a root is, sorry, not a multiplication property. I remember what a root is. So essentially what I'm saying to you is if I can't have that root down here, how can I get rid of it? Well, the beauty of the multiplication of 1. Much like you would take a fraction, okay? So if I wanted to take something, a little side note here. Say I wanted to take 1/2, okay? And I want to turn 1/2 into 5/10. Well, how can I turn 1/2 into 5/10 without changing the value? Remember that 1/2 and 5/10 are the same amount. Well, if I come over here and multiply it by the magical number 1, the magical number 1 is 5/5, which is 1, yes? So 1 times 5 is 5, and 2 times 5 is 10. This is what keeps, okay, this 5/5 here, this value of 1 is what keeps this and this value the same, but fractions are special because we can talk about different looks. So I have to apply the same principle to this. And the way I'm going to do that is I'm going to remember this. That if I have a root with some base, okay, being raised to the same index, okay, then that would just give me, the root would be gone. I would take the absolute value of whatever that base was. So, for instance, I currently have the square root of 2. Now, I want to get rid of the square root of 2. It's not helpful that it's down there for me because, remember, I cannot leave a root in the bottom of a fraction. It's just a rule that we have in mathematics. So, again, what I do is I apply this rule right here, okay? So I'm going to try to make the power of 2 match the index. So I'm going to put a little 1 in here to show you that that is 2 to the first power. And there's a little hidden 2 out here, okay? So what I have to do here is create something, all right, that is going to make 2 squared. Because if I make 2 squared, then the radical goes away. So we go back to a multiplication property where if I multiply this by root 2, okay, I have to also multiply the top. So what I'm essentially doing is multiplying the top and bottom of this fraction, or I'm multiplying this fraction by 1. So root 2. So I'm not going to change the value of it because I'm really only multiplying by 1. My 1 looks funky and it looks a little weird because it's root 2 over root 2. However, I now have 2 to the first times 2 to the first. And applying a multiplication property, okay, a multiplication property of roots that states that if I take a radical that has the same index as another one, that I can multiply the radicands together. So what I now have here is that this essentially is root 10 divided by root 4. And this is kind of an unnecessary step. I'm just showing it to you, but I want to prove to you something here that any radicand, okay, that completes its index amount. So if I take a radicand times a radicand, and that would become 2 squared, okay, then this would become a square number. So 2 times 2 is 4. Well, the square root of 4 is 2. So essentially what you need to remember really quickly is that any radicand that is multiplied by its completed radicand, whichever the exponents add up to, will always be what that base number is. So in this case, my final answer for this one is root 10, okay, divided by 2. And what I'm left with here is just simply knowing, okay, that 10 is not divisible by any square numbers. And I could go through the means of over here, but this is basically the bare bones of it. So this is what this division property is used. The first one here we used in example 1 to demonstrate I use this method if A and B have common factors. And this one here is just going to show you that if A and B don't have common factors, I can break it apart so that I can use this to rationalize the denominator. And then we apply this property here of multiplication of 1, and then we know that this simplifies. And that's simply that. So I hope that helps with understanding what these radicals are doing.